In today's lesson, we're going to take a look at logarithms. For those of you who did them last year, fantastic. This is going to be a good review for you. And for those of you who haven't seen them before, you are in for a treat. Logarithms are a truly beautiful thing to work with. They let you solve problems that were very difficult very easily. That said, they often do confuse the crap out of students. So we'll keep that in mind, and I'm going to try and start off easy and kind of work our way up. For the most part, it's a notation thing. If you can get over the notation, life should be good. So a logarithm is basically just the inverse of an exponential function. It's what we looked at the end of the last lesson. We just didn't know how to rearrange when we had switched the x and the y, how to get the y by itself again. So I'm going to actually just highlight this part because it's hugely important and even blow it up a little wee bit. And that's that normally we write an exponent in this form, where the base to an exponent is equal to an answer. So for instance, 2 to the exponent 3 equals 8. Well, that can also be written as the log of a base, and we write the base as a subscript, of the answer is equal to the exponent. So this is letting us actually isolate the exponent. Now, if we wrote this over here just as the example, I do not want highlighter to write in. Come back to me, highlighter. And now non-highlighter. Okay, there we go. 2 to the 3 equals 8. I could rearrange that and write it like this. Log base 2, because that was the base on our other side, of the answer equals the exponent. So this is a way of letting us rearrange to express the exponent by itself, especially if the exponent is an unknown. But before we get there, let's just try to solve or to look at some really easy versions. So here we have some exponential equations. 2 to the 5, 2 to the 5 equals 32. I'm just going to rewrite that as log base 2 of 32 equals 5. And what that's really saying is, for the base of 2, what exponent gives me this answer? So this one would be log base 4 of 81 equals 3. Log base 5 of 125 equals 3. And log base 10 of 100,000 equals 5. I will point out that on your calculator you have a log button, and the log, by definition, if it doesn't have a base, is automatically base 10, since pretty much everything we do in most everyday life is base 10. So if it's base 10, we actually don't have to write the base there. We just say log of 100,000 equals 5. It's the only base that we can do it that way for. There is another special base that gives you your ln button on the calculator, the ln, and that's base E, or Euler's number, which we mentioned once or twice so far. But again, we're not going to work with that one. We're going to stick with the logs. Okay, so to reiterate that, how come my calculator doesn't have a base on the log button? And the answer is it assumes it is base 10. And so the nice thing is, for some of these, we can actually do them on our own. Before you even pick up your calculator for this one, log of 1,000 is basically saying, what exponent do I put on 10 to get 1,000? And 1,000 is 10 times 10 times 10, so that would be an exponent of 3. And if you don't believe me, pick up your calculator right now, punch in 1,000 log, or log 1,000, depending on the order your calculator takes it, and the answer should be 3. Let's try doing the second one without a calculator. Of course, we could verify with our calculator, but let's try to do it without. What exponent would we put on 10 to get 1,000,000? And I think the answer is more or less obvious. It's 6. 10 to the exponent 6 is 1,000,000. Now, What about log 80? This one's a little bit trickier and it's not intuitive when you're doing ones like this. Log 80, I can't do that one in my head, but here's what I can do. I can point out that the log of 10, sorry, I didn't want to make that the base, although technically it is. The log of 10 is 1, and the log of 100 is 2. So the log of 80 is going to be somewhere between 1 and 2. I think it's going to be a little bit closer to 2 because 80 is a little bit closer to 100 than 10, but it's nonlinear, so it's a little bit tricky to think about. That said, I can now pick up my calculator and verify what the log of 80 will be. And sure enough, it's equal to 1.903. So we can estimate logs that are in base 10, or other bases for that matter. We just can't necessarily get it very precise. Could do it with a little trial and error. And I believe there are several teachers in grade 11 that teach the trial and error method, not for logs, but for unknown exponents, which is really the same thing, by guesstimating or squeezing between two values. Now the log of 20,000, again, I'm just going to kind of over at the side here write out that the log of 10,000 would be 4, and the log of 100,000 would be 5. So the log of 20,000 is between 4 and 5. I'm guessing closer to 4. If I had to guess, I'd say, I don't know, 4.1, maybe 4.2. But the good news is we all have calculators we can punch in. So the log of 20,000 is equal to 4.3. Okay, so a little bit higher than I suspected. I guessed 4.1, 4.2, but 4.3, okay, that's still reasonable. So again, it is super hard to estimate logs like this because it is a weird nonlinear system, but we can at least ballpark them between a couple of values if we had to do them without calculators. How can I evaluate logs that have different bases? Okay, log base 2 of 128. I'm just going to kind of do this to the side. 2 times 2 is 4, times 2 is 8, 16, 32, 64, 128. That works out really nicely. So 2 to the exponent, 1, 2, 3, 4, 5, 6. The answer should be 7. So that's doing it logically, but I want to show you another way you can do it. You can do log base 10 of 128 divided by log base 10 of 2. I'm not going to explain why this works right now, but I'm going to tell you it does. So the log base 2 of 128 is the log of 128 over the log of 2. So I type in 128 log, which gives me a number that doesn't matter, divided by the log of 2, which is a number that doesn't matter. And when I divide them, I get out 7. So these ones, if you can do them in your head by looking at it, if they happen to work out to be perfect, that would be fantastic. But if not, that's the trick. Do the log of the part you're taking the log of divided by the log of the base, both at base 10, and that's how you deal with different bases. So this one here, I think this one works out exactly. So 7 squared is 49, 7 cubed is 3, yeah, so that should just be a 3. 7 to the exponent 3 is 343, but I could always do log of 343 divided by log of 7. And again, don't worry about what the actual logs of the top and bottom are. Those numbers are irrelevant. It's just the ratio of them that matters. So 343 log divided by 7 log is 3. For part C, we're not going to be able to get this one bang on, but we can estimate it a little bit. 5 to the exponent 1 is 5. 5 squared is 25. 5 cubed is 125. 5 to the 4th is 625. And 5 to the 5 is, I don't know, over 3,000. So the fact that 1,000's between 625 and 3,000 something tells me that my log should be between 4 and 5. I have no idea. 4.5 maybe, 4.7, 4.3, doesn't matter to me. If I want to do this on my calculator, I'm just going to do log of 1,000 divided by log of 5. We know the top number is going to be 3. The bottom number is going to be, what is it, 0.69897 something. Doesn't matter. The ratio is all that matters. So when I divide those, I get 4.292. Okay, so as predicted, between 4 and 5, so we can estimate again, but getting them is tricky. Now for part D, the log with a base of 1.6 of 75, even estimating this one's going to be nasty because 1.6 is not something I want to try squaring and cubing and fourth powering and fifth powering in my head. So I'm going to skip that completely and go straight to log of 75 over log of 1.6. And the fact that it's a decimal doesn't hurt or change anything. The calculator do just fine on it. Yeah. So log of 75 divided by log of 1.6, and I'm getting 9.186, etc. And if you want to just check them, if you want to make sure that you're on the right track, just try it and see if 1.6 to the exponent 9.186 should equal 75, keeping in mind there may be a little bit of rounding error since we're using decimals. So 1.6 to the exponent 9.186 is 74.9973919. Okay, so it's 75. So that's the nice thing about these logs like this, is that even if we get an answer, if we're not sure about it, we can always double check it really easily using exponents, since they are just inverse operations. Okay, now what we really want this for is when we want to solve for variables. So these first ones here, log base 2 of x equals 4. That's saying the log base 2 of something is equal to 4, which means that, well, if I rewrite that actually as an exponential equation, I think it's actually going to be easier, because the log version says the base is 2, the exponent is 4, and the answer part is x. So converting from a log to an exponential makes this really easy, because I know that 2 to the 4 is just 2, 4, 8, 16. This one, the base is 3, the exponent is 2, and the answer is x. X is 9. No calculator required. Log base 5 of x equals 3 just means 5 to the 3 equals x. Oops. Where it is, x equals 125. And log x equals 3. There's no base stated, so remember that that's really a base of 10. So x is going to be 1,000. And again, you can always verify these in your calculator. So for instance, for this one here, you could just type in log of 1,000 and you should get 3. For part C, you could type in log of 125 over log of 5, and you should get 3. All right. So I have put here that you can always switch back and forth between the two versions. And also there's a couple restrictions on there that I've mentioned that are important to note. B has to be greater than 0. Okay, actually, let me deal with the second one first because I think it's more obvious. Why does it not work when B is 1? Well, if I do have B equals 1, that means I'm rearranging to get something that looks like this. 1 to the x equals, let's say, 5. That one I can't solve for x because 1 to any exponent's 1 is no solution. So if b is equal to 1, that will only be true if 1 to the x equals 1, and then x can be anything. So it's either going to be no solution or every solution. It's called hyperdefined, depending on the equation, but there's no real variable, to be honest. B can't be negative. The reason for that, and this is kind of weird, but if I think about an exponential function, b can never be negative. B can be less than 1, but it can't be negative. And the reason for that is if I said, for instance, y equals negative 3 to the x, it feels like that would be really easy to solve, right? But if I plug in x equals 2, I get out y equals 9. If I plugged in x equals 3, I get out y equals negative 27. Negative 3 times negative 3 times negative 3. What happens when I plug in x equals 2.4? If x is a fraction or a decimal, is the answer positive or negative? I mean, I could do the 3 to the any number part, but the negative part, I no longer have a negative times a negative or a negative times a negative times a negative. I have a negative times part of a negative. I don't know how you do part of a sign. So because of that, we can't deal with negative b values. Okay, I think I've probably confused you enough with that. If you're a little bit lost on what I just said, just be aware that b has to be greater than 0, but cannot be 1. At 1, it doesn't make any sense. So there are some questions there at the bottom of the page you're welcome to try. Let me know if you've got any trouble. Otherwise, I will see you in the next lesson.